one of the factors that control whether a nucleophuse dissociation, a DN step, is reasonable or not to propose. Well, really there are two, and both of them go back to this idea of charged species being those that actually control the reactivity of molecules in a deep and profound way. So generally in a DN step there are two charged species involved. There's the anionic leaving group, which can sometimes be neutral. We saw that in the example of the protonated ether. But if the leaving group is anionic, you do want to think about its charge and its stability as a result of that charge. The other is the stability of the resulting cation. So we talked about the factors that control the stability of cations, and those are going to come into play as you're thinking about, is a DN step reasonable or not? And generally, again, as I said, these steps are favored under acidic conditions. So if you see an acidic reagent, sulfuric acid, hydronium, H+, things like this, generally the DN steps will be more common in those cases. So let's look a little bit in more detail at these two factors that control the reasonability of the DN step. So what you're seeing here are two potential DN steps. On my right here is the leaving of a chloride, and on my left here is the leaving of a methyl group. Now the problem with the leaving of the methyl group is that the anion of methyl, the methyl anion, is very unstable. Remember our talk about pKa's in the context of proton transfer. That CH3- is extremely reactive and extremely unstable. As a result, it's rather unreasonable to take something fairly stable in this compound here and just break a carbon-carbon bond into two very unstable intermediates, the tert-butyl cation and the methyl anion. Now here, on the other hand, we have a reasonably stable neutral compound, but dissociating the chloride isn't going to be terribly unfavorable. In fact, it's going to be rather favorable because the Cl- anion is fairly stable, and if we can stabilize that positive charge that develops on the tert-butyl cation, then we have a very productive pathway, productive and reasonable mechanistic pathway. In thinking about the cations, one of the biggest factors that's going to come into play here, really there are two, and I've only really highlighted one of them here, is substitution. So on my left, or on my right, excuse me, you see a primary cation, which we learned is not very stable because of a lack of hyperconjugation from surrounding alpha hydrogen atoms. And on my left here, you see the tert-butyl cation, and this is a fairly stable cation because of a large amount of conjugation, of hyperconjugation going on in this molecule. So we would expect the formation of tert-butyl cation to be rather reasonable here, but the formation of the primary cation is almost never observed and really is never something that you want to invoke as reasonable in a mechanism. Now the exception to that rule is if the cation is stabilized by an adjacent lone pair or pi bond. So here delocalization comes into play. Won't say too much about that. Feel free to go back and review our talk about the factors that control the stability of cations, but delocalization can be a very important factor dictating whether a DN step is reasonable or not. What I wanted to do now was go through a few examples of the DN step, and what we're going to do is look at reactions that involve typically in the early stages of DN step, and some of the stages that follow that DN step typically. And so things you should keep in mind here is that the conditions for these reactions are generally going to be acidic, as you can see here, and that's because those acidic conditions, those very stable anions, are able to surround positive charges and stabilize them fairly well. A question you should keep in mind, and one that maybe is worth taking notes on if you're studying organic chemistry right now, is what steps tend to follow DN? So what steps do these reactive cations typically undergo? And we'll look at these in some detail in this lesson, and in more detail as we actually cover those steps in later lessons. Alright, so the first example I wanted to look at is the unimolecular elimination. And this is the formation of a pi bond from a leaving group and an H. So elimination is the formation, most generally, is formation of a pi bond from a leaving group and an H atom. And for the unimolecular elimination, the idea is that the transition state that is rate determining, the slow step transition state, involves only one molecule. And typically it's the first step, it's this DN step. So the slow step is a simple dissociation of the leaving group away from the electrophilic carbon. Now, this is very common for highly substituted electrophiles. So for less substituted electrophiles, you'll often see that they undergo E2 reactions. So just like SN2 reactions typically take place on less substituted electrophiles, E2 reactions also. And just like SN2 reactions are favored under basic conditions, E2 reactions are also favored under basic conditions. We'll talk about E2 in more detail later, but in looking at E1 here now, you see that there are some interesting issues with the regiochemistry here. So what you're looking at in the center here is a cationic intermediate in the middle, smack in the middle of the E1 or unimolecular elimination mechanism. And in this case, there are 9 hydrogens around this central carbon that can all leave in what's called a DE type step, we'll talk about that later, to form a double bond. And in this case, any of those 9 hydrogens gives the same product. But that's not always the case, and this is an issue of regiochemistry. There are different isomers that can potentially form from this reaction, and we want to think about how we can rationally control these isomers and their relative formation. And this goes back to our discussions of kinetics and thermodynamics. So we want to ask, can we use kinetic or thermodynamic control to really influence the direction and the selectivity of the elimination reaction? And so here's the fundamental problem laid out for you in the context of one substrate, the one shown here. So we can imagine this bromine leaving in an a DN type step, and if we do that, that would then generate a cation right here. Now that cation can receive electrons from several carbon-hydrogen bonds around here. I've highlighted 2 here in green and red. If it gets electrons from the green CH bond, then we would form a double bond here. However, if it gets electrons from the red CH bond, we would form a double bond in a different position. And the question is, how can we think about where it will be very likely for those electrons to come from? How do we know which CH bond will be reactive? And in this case, it's really an issue of thermodynamics. So thinking about thermodynamics, we can recognize that because the double bond formed between these 2 groups, because the vertical double bond here is attached to what would be 3 groups with the bromine gone, whereas this double bond is attached to only 2 groups. Here we have 2 H's, 2 carbons I should say. Then we can recognize that the more substituted double bond will be the more stable one. As a result, we would expect more product to come from elimination of the green versus the red hydrogen.